Okay, so welcome to the second lecture. First news is that the video of the first lecture is already up on my YouTube channel, and later today I hope the notes for both the lectures will be available on the blog page. It will be nice if somebody posts a question or a comment on that blog page just to see if it's working. So far I haven't received any. Has anyone tried? I guess not. Please. Okay. But just try, because it should come to me for moderation, so that way I'll know whether it's even working. Okay. Good. Let me add a couple of things to what I did yesterday. So I started yesterday by talking about vector fields V equals V mu d by dx mu. I should have emphasized that if V mu are constants, then this is a vector at a point. And if they are functions of x, then it's a vector field. This we all know. A field is something which has values everywhere. An simple object might just be defined at a point. So this is a vector field, but it's easy to generalize to a tensor field, T. And what I can do is just give it p different indices. It will still be a function of x. And here I'll take a formal tensor product of p terms, so it's a rank p tensor. And like vector fields, tensor fields defined in this way start out their life with all upper indices, but because we have a metric on the manifold, those indices can come down using the metric. So one thing that most physicists don't learn is that you can also study differentiable manifolds without having a metric. A metric is like a next step in differential geometry, and so if you don't have a metric, then vector fields and tensor fields are stuck forever in life to have indices only up, and the guys who can have indices down are the differential forms. But once you have a metric, you can just go back and forth. Now notably here there is no symmetry or anti-symmetry in these indices, because formally this tensor product is just over independent copies of the space, and you cannot exchange, there is no symmetry under exchanging any two. So these indices are just generic. So you can accommodate symmetric or anti-symmetric or whatever you like in this. Now with differential, so these are, let's give them their name, these are vector fields, these are tensor fields. On the other hand, if I have differential forms, what I defined last time, and I forgot to say this, is that a differential form of this kind is actually a one form. So analogous to a vector field, it has one index and that index is down. And you can likewise have differential forms with many indices. So I can have a differential form that is, I don't know, p of x will be mu1 up to mu p, and lots of dx's. Now again, you could in principle tensor them like this, but those would not be called differential forms. Differential forms have a very special feature that we multiply them with a product called the wedge product. So this is called the wedge product, and it is antisymmetric by definition. So for example, dx mu1 wedge dx mu2 is declared to be minus dx mu2 wedge dx mu1, and the same for any two. You can also interchange them, like you can exchange 1 and p if you like, and you'll still get a minus sign. Actually, you may or may not. If you want to exchange 1 and p, you have to take mu1 and hop it over mu2, mu3, mu4, and the number of minus, you'll get a minus sign each time. So in the end, you may have a minus or a plus sign depending on how many there are in between. Okay, but whatever it is, this fact gives an total antisymmetry to these things. So the components of a differential form are totally antisymmetric. Now you could ask, why did we limit ourselves like this? And the answer lies in the usefulness of what is called derive cohomology, which is a structure associated to differential forms. Yes?
I think the overall there will be just a minus sign, right? If you swap any two.
I see. Yeah, sorry. Thank you. Thank you. Yes.
Because once you will have to go through n times, the other one will have n minus
the same number.
N minus 1 times.
N minus 1.
So 2n minus 1 it will be.
I had a momentary brain freeze when I was a bit confused. But yes, if I want mu1 to go to the last place, then it depends on the number of things it goes through. Yeah. But if I want to exchange mu1 with mu p, after I do that, I have to bring mu p back, and there's one less thing it goes through. So the net number is odd. Thank you so much. That I just suddenly got a little puzzled by that. So yes, any pair you exchange will always be minus. But if you want to move one of them without touching the others to some other place, then you'll just get a bunch of minuses. This is correct. Thank you. Components of a differential form are totally antisymmetric. Yeah, so I was saying that there's a reason for it which is deep and has to do with topology and things that we are not going to discuss, at least certainly not now. But that's how it is. And for this reason, P has to be less than or equal to the dimension of the manifold, because if we have more than D indices in B and they're all totally antisymmetrized and each takes D values, then it's just 0. Not only that, if P equals D, it's very interesting. Then the only thing we can have actually is the wedge product where each X appears once and only once, and you can always get it into this order up to a sign. And it's a very interesting object because in differential geometry, this is used in the definition of a volume form on the manifold. And if you have a metric, then to be precise, you multiply this. So first thing is, given this total antisymmetry, it's really like a scalar in that it has only one component. It's not a multi-component object, because a P form has D choose P components. So if P is D, then you have D choose D, which is just 1. So there's only one thing. And if I multiply by this, then it's actually invariant under general coordinate transformations. That preserve orientation. So I don't want to go into details about orientable manifolds. We did mention them briefly last time. But you can sort of imagine what orientation means. And it's only on orientable manifolds and with a choice of orientation that you can define integration. And this volume form is what helps you define that integration. So the integral of just this thing is the volume of the manifold, and then you can integrate other things. Good. Okay, this is just some remedial things that I missed to say yesterday. And now I'll go straight back to our frames. Are there any questions on these very simple things? Okay. So yesterday we defined, we'll go back to frames. We define EA mu and EA mu, which is obtained from it. And the other two, which are where you raise A and lower A by the Minkowski metric. And then we have these two main identities, EA mu is G mu nu, and EA mu EB mu is eta AB. So if I contract this pair of indices, I get G. If I contract this pair, then I get eta. Some references use a different notation for the guys with mu up versus down. It could be important. It's not going to be for us, but some people use small e and capital E, for example. And well, the det of this, as you know, is square root of det of that, but det of this is inverse of det of this. So that det of that is 1 in magnitude. Okay. So now, yesterday we noticed that the covariant derivative of this had 3 terms. This and then I think this is right. Yes. And we set this to 0 and we called it the no torsion condition. And I said that, and I stopped at the point where I said that we can use this to solve for the spin condition. So what do we do? Well, this is of course the Christoffel symbol and it's given in terms of the metric, but the metric is again given in terms of the frames by one of the equations, this one. So this is frames, this is frames, this is frames, this is the only unknown. So I can try to solve it, and it's a straightforward exercise, and you find the nice result that omega mu A B is equal to minus E A mu. I'll explain the notation in a second. Yeah, some comment? Yeah.
Can you explain why this is called spin connection? What it has to do something with spin?
Good. Okay, so actually I don't really know the answer, but the important thing is that it's a connection for the Lorentz group because these are local Lorentz indices. So it's a connection for the Lorentz group, which is an orthogonal group, SOD minus 1, 1. Now, orthogonal group is, as you know, it's just a family of Lie groups, and we are mostly familiar with the algebra of the orthogonal group, which is unique and somewhat straightforward. But given the algebra, there can be the orthogonal group, which technically, as I understand, only has tensor representations like vector, second rank tensor, third rank tensor. But there's a kind of extension of the orthogonal group called the spin group, which is the same as the orthogonal group when it comes to the algebra, but it admits double valued representations, which are the spinor representations. Half integer, exactly. Half integer is only for the four-dimensional or three-dimensional case. In higher dimensions, it's half integer values of different Cartan labels of the representation. So a little more complicated, but there's a well-defined concept of spinor representations. So there's one family of representations called spinor and there's another family called tensor. Okay, with the rule that whenever I take the product of two spinor representations, I always get the tensor ones. It has a nice boson-fermion kind of property. Tensor representation in field theory are always used for bosonic particles and spinors for fermionic particles, if and only if. So because that is the spin group that it's a connection for, I think might be the reason it's called the spin connection.
So is it like this omega is transforming the spins in some like internal?
Yeah, at the moment it's not doing that because see, these being local Lorentz indices, E is actually a vector of the vector representation. It has one vector index. It doesn't have a spinor index. But we'll see in a little while, actually maybe today itself, that if we want to couple fermions to gravity, then this same guy with something multiplying it will become the connection that acts on fermions.
And this
So
will
it's not this by itself doesn't have any info about spin representation, spin or representations, but it can be used to be a covariant derivative on spinners.
But this will always be function of metric.
Not metric, it's a function of the spin connect of the frames, not metric. So one exercise I've given in the notes, you see the frames, let me just mention, thanks for the question. The frames have d of these indices and d of these indices. So and it's a d by d matrix, but there is no possible symmetry because there are even different types of indices. So there are d squared components. Now the frame, if I know the frames, I certainly know the metric by that bilinear relation. The metric has d into d plus 1 by 2 independent components, which is a lot less than this. So the frames contain something more. The exercise, which is very trivial and maybe some of you already know the answer, is what is that some more information and how can you show that it accounts for exactly the remaining, if I subtract this from this, which is d into d minus 1 by 2. Okay, degrees of freedom. This means that from the frames I can reconstruct the metric, but from the metric I can't reconstruct frames. There's more information in frames than in metric. And therefore, when I say omega is, if omega was a function only of the metric, I couldn't find it from this equation because I need to know the frames to find this, right? So this is this. Now I need to get rid of this E. Now it's these are all invertible matrices. That's the easy part. So I can multiply this by E with a lower new index and get rid of this. Then I'll have E multiplying those, and that's the equation I was about to write. So that determines this as a function of E, not of G. Unlike the affine connection gamma, which is a function only of G.
Is this restricting too much?
What?
This no torsion condition?
No, I don't think so. I made that comment yesterday that these kind of quantities, if we want to, the point is that if this was not zero, it would still be a tensor with two spacetime and one Lorentz index, but it's a tensor. It transforms as a tensor. So I could give that tensor a name. It's called the torsion tensor, and it could be just treated as a separate object. There's no need to impose that this is equal to some new tensor. If I had such a tensor in my theory, that's fine. I could just treat it as a different object. And it's much more convenient to work with this being zero, because if it's not zero, then of course I can't find omega in terms of E. Then omega is determined in terms of E and that unknown tensor. It's just like having too much more data than you really want. Yes?
So this information, d square number of components, the rest of the component goes to this omega, right? This d into d minus 1 divided by 2, because this lower a, b are antisymmetric.
Well, omega is actually got d times d into d minus 1 over 2, so it's not
so
really...
contracted this dx.
Yeah, I wouldn't like to say it that way, but anyway, we can talk about it later. Okay, let me finish this statement. So this is equal to this, where this nabla bar or del bar or gradient bar is by definition the thing which doesn't know about local Lorentz indices. So it just treats E as a vector with one lower index and it doesn't care about that. So therefore by definition it's del nu E B nu minus gamma mu nu lambda E B lambda. And it's almost obvious, it's just by solving that. So the first two terms are actually nabla bar of E, and then the last one is omega, and so you get this solution. And just one word about references. I keep saying I'll give you references. So let me just mention some references particularly on this subject. One very good one is the physics reports of Eguchi, Gilkey and Hansen. I can't tell you when or anything, but I'm sure you know how to figure that out. It's called something like gravitation, gauge theories and differential geometry. What I like about it is that it relates many of these formalism things to physics situations. It might be some interesting non-trivial manifold like Taub-Nut manifold, or it might be Yang-Mills, or it might be something else. And they have lots of very good examples. And also these are three people who developed this field of gauge theory on the mathematical side or the formal side in very nice ways. There's of course Wald, and you know the book, I forget what it's called. What is it called? General Relativity. Okay. I use Wald a lot, of course. There's Hawking and Ellis, but I don't know if Hawking and Ellis has anything about specific or much about frames. It's also a notoriously hard book to read. Now, comment about Wald is that for him, the covariant derivative is always this one. He never uses that one. Okay, so there's a notational issue. He won't put a bar, and for him, it always differentiates the space-time indices and never cares about the local-Lorentz indices. But that means that his covariant derivative acting on a local-Lorentz vector or tensor will not give you back a local-Lorentz vector or tensor. And that's unfortunate. And I think it's very important to decide that the whole idea of covariant derivatives, you can act on anything and you'll get back another thing that transforms properly as its indices would suggest. Good. So this solves omega, and then of course in the notes there's a long expression. If you expand out everything, you'll get a certain expression, and yeah. So if you expand out everything, including this in terms of frames, in terms of the metric, and then replace the metric by frames, so it's a tedious but straightforward calculation. So there's an answer for omega directly just in terms of frames. Okay. Now we're almost done with frames, but one notational thing. And again, this is Wald. But again, Wald got it from some old literature. I could take omega mu AB, and I could, for whatever my personal reasons, act on this index with a frame, and I could call this omega CAB. Now all its indices are local-Lorentz, and this goes by the name of Ricci rotation coefficients. I have no idea why. This is the name, but this is the name used both in Wald and I think in the, so this plays a role in derivation of the Kerr metric. So the original papers of Kerr and Kerr-Schild, I think, make use of Ricci rotation coefficients. And it took me a while to realize that it's something we know extremely well, just dotted with a frame. It's not a big deal. Okay. Yeah. Now you could ask, armed with all this formalism, you could ask the following very sensible question. We know that if I take two covariant derivatives and commute them, and if I put here a vector field, then I'm going to get Riemann times that vector field. We discussed this yesterday. What if here I put instead a local-Lorentz vector? What will I get? Now it's pretty trivial because this is E A mu A mu, and E can pass through these because of Fierbein postulate or the vanishing of the torsion. So actually it's just E A mu on the answer. So it's not very it's not very surprising. But let's just say that this covariant derivative is written as R mu nu AB AB. So this we can show that this we can take the following point of view. First we'll say we don't know what this is, but we'll just write it this way, because the ordinary derivative part cancels, whatever else is left we can write this way. But it's very obvious that R mu nu AB is nothing but our old friend R mu nu lambda sigma with E A lambda and E B sigma. So it's another way of getting the Riemann tensor, but surprisingly it contains a little bit of illumination. First of all, this one has antisymmetry in this pair, exchange of the pairs and cyclic symmetry. But this one has two indices of each kind and you can't exchange them. It is antisymmetric in mu and nu, that's true. It is antisymmetric in A and B if you bring them both down, that's also true. But you can't have any exchange between the first and last pair, and also you can't have a Bianchi identity. A cyclic identity. Bianchi identity actually you do have, as we'll see, but not a cyclic identity. Okay, that's one observation. Another observation, R mu nu AB being antisymmetric in two indices is naturally a matrix valued two form. So we basically try to make this property a virtue. The two form is called R and it has indices A and B, and it's half R mu nu AB dx mu wedge dx nu. So in this version, the indices mu nu have vanished because of this contraction. So this makes it clear that it's a two form, but it's also a matrix in the local-Lorentz space. Good. Now we can ask the question. So now we can just how to say it? We can, okay, so this is one notation where I show the indices A and B and I hide the indices mu and nu by doing that. I can also use this notation where I show the indices mu nu and the indices A, B are matrix valued. Okay. Now those of you who do know Yang-Mills theory will realize that this notation makes it very similar to the Yang-Mills field strength, which, as you know, we often write like this, and these are the generators of, people know this, some people definitely know it. So these are the generators of your gauge group, and instead of showing their matrix indices, we'll put that tilde to show that it's a matrix. And now you can see that these things look somewhat similar. And that's not all. A very lovely exercise is that in this notation, you can show, it's very simple actually, that R mu nu, the matrix in this local-Lorentz indices AB, is nothing but del mu, the spin, so the spin connection can likewise in this notation be treated as a vector, because it is omega mu AB. So again I suppress A and B and I treat it as a matrix in the internals in the Lorentz space and a vector in the space-time. And so it is this minus this plus this. And this is precisely the analog.
So how do you suppressing this A and B? One is upper and another is lower.
Yeah, so makes it a matrix. So now it's clear that I can multiply matrices. So for example here, so if here in this equation there's AB hidden here, AB here, AB here, but here there's AC, CB. Just in one up and one down is the best way to multiply. If they are both down or both up, technically you can't multiply them. So it always makes sense to have.
Raise by eta and then multiply.
Yeah, you raise by eta. That's why I started by choosing R to be like that. So I should have said this, it's just I forgot, that in the same way omega AB underlined, not underlined, omega, sorry, omega, so we can write again, omega AB is omega mu, it's again a one form. Just like this is a two form, that's a one form, so it's analogous to that. And omega mu is a matrix, and this is just omega mu AB. Or maybe the more correct way to say it is that the AB components of this matrix are the numbers omega mu AB. I think this is more satisfactory. So you got everything now, and this formula is true, and it's analogous to F mu nu in Yang-Mills theory equals del mu A nu minus del mu A mu plus. This plus or minus depends on conventions. I think here we are working, so yeah, I think this is okay.
Sweet.
Yes.
Yeah, how are you defining this R tilde? What is the definition of R tilde?
R with the under tilde is that it's a matrix whose AB component is R mu nu AB. It's just, it has four indices, two spacetime, two matrix. If I suppress the matrix indices, then I put a tilde saying that for every value of mu and nu I have a matrix whose matrix element is labeled by A and B. So again, if you want, it's the same equation, let me write it here. This matrix AB component is R mu nu AB. These are just different ways to interpret the same object. Okay, I could suppress all the indices and say R is a matrix value 2 form. But in this way I show the spacetime indices, and in this way I show the matrix indices. But see what a beautiful result, that the Riemann curvature 2 form is the field strength of the spin connection 1 form, in exactly the way that the Yang-Mills 2 form is the field strength of the Yang-Mills potential 1 form. But there is a very important difference. In field theory, this 1 form is fundamental. It is the fundamental field of the field theory. But in gravitation field theory, this is not fundamental, but instead is given in terms of frames. And I guess I had it somewhere. No point showing you again. You know that omega is determined in terms of frames completely. So it's not the fundamental field. So for example, if you could do a path integral for Yang-Mills, the path integral measure would have dA, but for gravity it would have dE and not d omega. This is a very important difference. By the way, one little amusing sidelight. This actually came up in a bunch of research papers. We certainly want the determinant of E not to be 0, because we certainly want the determinant of the spacetime metric not to be 0, otherwise spacetime starts having 0 eigenvalues, which is terrible. That means that there are some directions along which distances are all 0. That's a singular metric, so we want this. And that's a constraint. So if I did do a gravity path integral, I should make sure I am not going to sum over singular metrics. But in Yang-Mills theory, there is no analogous statement, because I am summing over all vector potentials, modulo gauge transformations, but there is no concept that it is made up of a singular or non-singular metric. So this came up in a paper of Witten in the 90s or 2000s, I think 90s, on 3-dimensional gravity. And at first he said, well, it might be interesting if that E actually can be 0, because it seems like some topological phase of gravity. But then somewhere there's a footnote which says, I thank Nati Seiberg for pointing out that det E should never be 0. So it seems like it's a constraint we must put in gravity. Yeah.
But there can be 0 modes in Yang-Mills vector potential, right?
Yeah, the vector potential is a different object from E and mu. Vector potential is a matrix valued one form, and it can have any, it can be zero. Of course, in vacuum the vector potential is zero.
Same as in we are having 0 modes.
No. In vacuum G is not zero. In vacuum G is eta. And G can also be non-trivial in vacuum, but even the most trivial G is the Minkowski metric. It's not zero. It's in a way it's rare. Like all normal fields can be zero. Scalar field can be zero. It may not be stable. It might have an expectation value, but can be zero. Fermions normally in vacuum are zero. Vector fields can be zero. You can just have empty space with nothing. But if you have empty space with nothing gravitating anywhere near it, then the metric is eta rather than zero. It's Minkowski. It's not
so
zero.
The analogous thing from Yang-Mills, which is, let's say, vector potential. The analogous
No, vector potential is not analogous to E. It's analogous to omega. The spin connection.
Yeah. So how are these two different? What was your?
I said the difference is that this one is a fundamental field, and this one is derived because it's a function of E. So there is no analog of E in Yang-Mills theory from which we can get A. A is the basic object. Just in Maxwell theory, which is a trivial example of Yang-Mills theory, and that term isn't even there, A is just the photon field and its components are the vector potential and scalar potential. In the old days, people thought E and B are fundamental, then they said no, phi and vector potential are fundamental, but nobody so far has made the next step to say that phi and A should also be derived from some other thing. Maybe it's true, but it seems like we get very good results assuming phi and A to be fundamental, because we do the path integral from electromagnetic dynamics using that. Yes.
Is this because we are not having any like the analogous statement of no torsion condition in?
No, it's because there is no analog quantity of E. There's simply no object in Yang-Mills theory which is one form and has another index of some different type, and which is a vector of the gauge group. E is a vector of the Lorentz group.
Yeah. But there is this condition as well, no torsion condition, right? Which you
That
are imposing.
No, but the no torsion condition did something different. It solved for omega in terms of E, but even suppose we didn't solve for omega in terms of E, we might still get an equation like that. So this is about a relation between matrices, that is adjoint representation of the Lorentz group. E just isn't. So there is nothing, as I said, there is nothing in Yang-Mills theory which is directly okay. Of course, there are matter fields can be in vector representation of the Yang-Mills group, but the vector potential is not derived from a quantity in the vector representation. But maybe you will think of some weird reformulation of Yang-Mills theory which does that. Okay, so yes.
It's like because we have a relation between omega and E, why could we not say that omega is the fundamental object and we write E in terms of omega?
We actually can't, I think, because I don't think we can. Can we? E?
We could invert the relation and then we can say omega is a fundamental object in this.
Yeah, I'm not sure. Let me think about this. It doesn't seem right somehow. I don't think you can solve for E in terms of omega. Right. Omega is a derivative of E. So E cannot be a local function. It would be an integral of omega. So it won't be a local function. That's the problem. Exactly. Okay. So now let me close this discussion with two simple and almost obvious formulae. Under a local-Lorentz transformation, you won't be surprised to find that omega mu, the matrix, goes to lambda, which is the matrix of local-Lorentz transformation, omega mu lambda transpose plus lambda del mu lambda transpose. And this is a familiar formula in Yang-Mills theory, which is the finite gauge transformation of A. We often write it as U A U inverse plus U del mu U inverse. Sometimes there are I's that depends whether your generators are Hermitian or anti-Hermitian, but this is the relation. This shows that omega is a connection. It doesn't transform homogeneously, but also has an extra term. On the other hand, R is like the field strength, and it's supposed to be a good tensor under the gauge group in the adjoint representation of the gauge group, and so so R simply transforms homogeneously. These are all exercises you can do. And finally, there's the Bianchi identity. And there's really no work involved in deriving these once we realize that these are all fundamental formulae of any Yang-Mills-like system, where you have a vector which transforms inhomogeneously, and field strength which transforms homogeneously. And these all these. This is the covariant. And in principle, it's the full one, but you'll see that some of the terms cancel, all the terms actually cancel. So in principle, this should be expanded out to be the covariant derivative with Christoffel for these and with spin connection for the hidden matrix indices. Then you add up everything and you get 0. Okay. Good. So are there any questions up to here? We're actually making good progress. So this lecture and yesterday's are the ones that are just to establish a bunch of things, and from Monday I will start on geodesics, and then it will become much more interesting, and hopefully you won't already know it. To complete the discussion, so questions? Yes?
Yeah, are these equations which resemble Yang-Mills equations of trivial equations, are these connected to some n of SUN?
No, they are connected to SOD minus 1, 1. That's the point. You don't have the option to choose your gauge group in this case. The gauge group is given to you as the Lorentz group.
SO, okay.
And it's SO, not SU. And it's in particular for a D manifold, it's SOD minus 1, 1. So for example, the range of these indices as well as the hidden matrix indices AB, all of them go from 1 to D or 0 to D minus 1. While in Yang-Mills case, they're completely decoupled. The space-time indices go over dimension of space-time if this is F mu, and the Yang-Mills internal indices go over N, or for any SUN or any other group you could have E7, E8, SPN, whatever you like. So that freedom of Yang-Mills is not there in this case. Also in Yang-Mills we normally choose a compact gauge group, and here we are given the non-compact gauge group, so that is also a difference. Yeah. Okay, so I think that we are halfway through today, so I think there are two things I can do, and both of them will be doable in this time. Still, if there are any more questions, please ask. Good. So one thing I just want to get out of the way, and I realize now that I should have done it before starting on frames, because it logically doesn't rely on frames at all, is isometries and killing vectors. So I'm assuming that you know the basic idea. Under an infinitesimal variation of the coordinate, infinitesimal but local, so there's a vector field along which the coordinate is reparameterized, if you like. The metric changes, of course. We know how the metric changes, and we'll define delta G mu nu to be the new function but evaluated at the original point minus the old metric at the same point. Okay, of course what takes part in the transformation law is g prime of x prime is some del x prime by del x factors times g, but of course since this is infinitesimal you can always shift x prime back to x at the cost of an extra term. Just expand, Taylor expand to lowest order around x. But it's this which is defined to be delta g. And it is this which, if it's 0, that implies that V mu, the vector field V, is an isometry. This is the definition. Of the manifold entity. So this is in some way a passive way of viewing it, because I stay at the same point, but I ask myself, I had a metric, now somebody has effectively changed the metric to a new function, but it's the same function. So that's one way of saying it. The active way would be to say that I'm on a manifold and I move a little bit and I find that everything around me looks the same as it did before. That's maybe an intuitive picture of isometry. Isometry, of course, means same metric. Iso and metry. Metry is the metric and iso always means same. So it's a isometry of a manifold, and it's very important to realize that generic manifolds need not have, in fact, generic will not have any isometries. There is no need for a manifold to have any isometry. You can just take a two-sphere and hammer it, dent it from all sides, and it just won't have any isometries. Even if you dent it a couple of times, it will lose all isometries. If you deform it to be an ellipsoid or egg shape, then it will have still one rotational isometry, but you can get rid of everything. Or you can keep it a sphere, which is it's a very symmetrical object, and you will get lots of isometries, one for every axis. So that's quite a few isometries, and in a few minutes we'll prove a theorem telling us what's the most number of isometries we can have. But for that we need two very important equations. So what we do is that we insert this variation, evaluate the change of evaluate g prime using the equation g prime of x prime is g of x times some these factors, differential factors, then shift back to x and set this to be 0. So we'll get a condition on V. Now that condition, curiously, even though V starts its life as a vector field, so its index is up, the condition on V for there to be an isometry turns out to be naturally best written with its indices down, and it's this equation. And it's called the killing equation. So this is an exercise for you. It's everything you need for the exercise is on this board except the transformation law of G, which I'm sure you know. And it's a very beautiful equation. In particular, given this equation, you can take its trace and you find that one property of the, so if it's the killing equation and any vector field satisfying it is called a killing vector field. Okay, and killing vector field, KV for short, is always divergence free. But of course, this is a stronger condition. It's not only divergence free. It actually says weirdly that this derivative, the gradient along mu of V nu, is minus of the same thing with the indices reversed. It's an important exercise and not totally trivial. So if you haven't done it, you really should do it. One interesting thing is, remember this equation has a couple of affine connections in it, and they don't drop out, and you'll get those exactly when you take g prime at x prime and shift x prime back to x, then you'll get a derivative of g, first derivative, and then when you assemble the derivatives all correctly, that's when you will get the Christoffel symbols. Good. So this is one very important equation. And there's a second equation which follows from this. It follows from two things. One is the Killing equation and the other is the commutator. So first let me write it. Del, it's a second order equation. Del mu V lambda is equal to R beta mu nu lambda V beta. And this is where R is the curvature. This is called the Killing vector lemma. So these are two important equations that the Killing vector satisfies. If you take this and you combine it with the equation which says that commutator of two covariant derivatives gives you a Riemann tensor, then you derive this. So all it's not given in the notes, it's left as an exercise, but the method how to do it is sketched in the notes. So you'll be able to do it, I'm sure. Now it's very nice, and we'll see this pattern happening a few times. You have a first order equation which involves the metric and the connection, but not the curvature. You have a second order equation which involves explicitly the Riemann curvature. So there are many nice things to say about this equation. First of all, second order differential equation. And Wald has some nice comments about it in his book, and he even has a paper about it. So, comments that you can make about it. One, suppose we know, so it's a differential equation, how would we integrate it? Well, we'll need initial conditions. So let's assume we know V mu at some particular point P of the manifold. That's not enough, it's a second order differential equation. So we should also know the first derivative. So let's got this lambda also at P. So for some point P, we can think of it as the initial point. Then one can argue that this differential equation can be integrated to determine the vector field given the curvature tensor of the whole manifold. So it's uniquely determined by these initial conditions.
How can we get the whole manifold from a single point? You have to specify the boundary.
We don't get the whole manifold, we just get the vector field. We solve for V.
Okay.
It's a particular vector field, it's a line in the manifold.
Okay.
It's a Killing vector. So basically, if you want to imagine, how you integrate a differential, how does a computer integrate a differential equation? It says, okay, I know what is V and gradient V at this point. Now I use this data to push it a little bit. Now I know it at this point, I push it a little more, and you get a line. And that's what we want.
Yeah. Why is it called lemma? Killing vector?
I don't know, just call that. I never understood what's the difference between a lemma and a theorem. I believe lemma is a little less serious than a theorem, but it's called Killing vector lemma, so it's famous. Yeah.
So the killing vector equation, that was first order.
Yes.
But so it seems like specifying two initial conditions seems like over specifying.
Yeah, but no, actually, the point here is that here we are given the curvature of the manifold and we want to solve for the Killing vector field in terms of that curvature. Okay, the Killing vector equation actually only tells you that the gradient of V in an arbitrary direction is antisymmetric. That means the gradient mu V nu is minus of the reverse. And in fact, that means that this also should be, this initial data should be antisymmetric. If I lower lambda, then I'm not allowed to give any gradient of V. I have to give at this point P such a gradient that this on V lambda is minus of this lambda on V mu. So that first equation just constrains what kind of gradients we can have. But this equation now actually can be solved because the right side contains the data of the manifold. And yeah, and now this, so this is one comment. And there's a very useful outcome. So now to count the maximum number of killing vectors, we can just count the total number of such data. You see, let's assume first that there are no killing vectors. Then I'll never be able to find a V such that gradient mu V lambda is minus gradient lambda V mu. So that's end of that. So it's not guaranteed that I can find such initial conditions. But let's say the manifold wants to be as symmetric as it can be, and therefore all these initial conditions exist and are independent. So let's count them. There are D initial conditions on V because it has one index. And how many initial conditions correspond to gradient of V? D minus 1 by 2. What do I get when I add these numbers? D plus 1 by 2, and that's your answer.
Sir?
One second. Let me just finish this thought and then take the question. And this, I claim, is the maximum number of isometries of any D manifold. D manifold, I mean a D-dimensional manifold. And we already know examples. SD, the D-dimensional sphere, has precisely this number of isometries. And why? That also we can prove. You might not be used to studying D-dimensional spheres, but the sphere gets its isometry from rotations in a one higher dimensional Euclidean space, and all we need is a plane. But there are exactly D minus 1 by 2 in equivalent two planes. But now put D to D plus 1 because the sphere is embedded in one higher dimension, and you get this number. And so it all works out very nicely. Yes, question?
Sir, so like you mentioned that we need two initial conditions. I still don't understand why. Because the data for the manifold is already in the metric, which is in the killing equation, the first equation. Right? So, and even for a sphere, we can like derive the killing vectors from that. So why do we need these two initial conditions?
So we are trying. Okay. So I think let's unpack your question. Clearly, if we want to solve the second order equation, we need two initial conditions. You're saying why can't we solve the first order equation, the killing equation? If okay, I could, but it doesn't give me the. So it certainly, if on a manifold, if you can find a V mu that solves the killing equation, you're done, and that V mu must also satisfy this. Okay, but supposing you don't. Supposing you instead know the Riemann tensor of the manifold and you want to construct the killing vector, then this is a way to do it. Actually, there's a very nice analog to these pair of equations we'll see in geodesics. There's a first order and a second order. They are useful for different things. But I think the question is good. I need to think a little bit more. Certainly, I mean, if you, for example, if I give you coordinates of a sphere, you can solve del mu V mu plus del mu V mu and equals 0 and find the killing vectors. I think the problem is, I'm not sure. Yes.
Just the killing equation does not contain any data about the curvature of space-time, right?
Well, implicitly it does because the metric is in it. Metric knows the curvature, but the equation doesn't directly have a expression in terms of curvature. I'll give you, you might know that there are coordinates at a point where the first derivatives of the metric vanish, Gaussian normal coordinate or Riemann normal coordinates. Then the Killing equation is just ordinary del mu v nu plus del mu v mu equals 0, and it doesn't have any information about the manifold. But there is no coordinate system in which this equation fails to know about the manifold because R is a tensor. So it has certain advantages. Okay. Now there is one more equation you can derive from the Killing vector lemma, which I don't want to send away. So this is done. Max number we've counted. We are going to use that max number in future. I just told you that examples of maximally isometric or maximally symmetric space are spheres, but I'm sure you have heard that this is also true of de Sitter and anti-de Sitter spacetimes, and even Minkowski if you count translations. And so that's all we are going to discuss, all those things. Let's take this equation and trace over the first and third index. This is not a bar, this is something like this thing. So del mu v mu, if I do that, I get the Ricci tensor there. So this is a consequence of Killing vector lemma. And this is pretty interesting because let's suppose that R was Ricci tensor is 0. Now we haven't discussed any physics yet, but as you know, the vacuum Einstein equations just set R to 0, R to index, Ricci to 0. So if that's so, then this is 0 for a Killing vector. But a Killing vector, this thing is antisymmetric. So from this, I get that del mu v nu is 0. First I set this to 0, then I use the Killing vector equation to interchange these two, and I get this. Okay, so v, the 4 vector v, the Killing vector, the tangent vector that along an isometry has vanishing Laplacian, harmonic, whatever you want to call it. Now, where have we seen two equations before? One is divergence of V is 0, and the other is this. These two. These are two. This one is by tracing the Killing vector equation, Killing equation, and that one is tracing the Killing vector lemma, and then setting R to 0. So this equation and this, we have a vector field which is divergence free and satisfies Laplacian on it equals 0. Where have you seen this before? Lorentz gauge, thank you, Maxwell's equations. Exactly in Lorentz gauge, this is Lorentz gauge, and this is Maxwell's equation in Lorentz gauge.
No source.
Yeah, source free, thank you. So it's a cute fact, and Wald has mentioned it in his book, but he's even written a paper on this fact, trying to make it trying to extract some consequences from that. Obviously there are consequences because this is a well-studied system. Maxwell's equations and Lorentz gauge we already know a lot. So of course now these are not flat space Maxwell's equations, these are curved space Maxwell's equations. But still, analogies like this can always be nice. Okay, good.
But
Now,
what consequences are there? Like, can you just...
I haven't read Wald's paper. I'll refer you to his paper. Okay. Good. We still have a little bit of time. Yes. Good. Now, good. So now we are going to change track, but we'll go back to local-Lorentz frames. And we'll try to address the question of how to couple fermion fields to gravity. Let's just take a Dirac spinner.
So you are working on 4D, right?
No, not necessarily. Dirac usually is, the term Dirac spinner usually means the one which doesn't have any reduction to either being chiral or real. So the while condition makes it chiral, the Majorana condition makes it real. In some dimensions like 4 you can do one or the other, but you can't do both. But in 2 and also 10 you can do both together, so you can have Majorana while. In odd dimensions there is no while, but you can still consider Majorana.
18, 26.
Yeah, exactly. Yeah, well, it's particularly easy to see in 2 dimensions, which is the best way to learn spinners actually, because everything is very transparent in 1 plus 1D and has to be done carefully, of course. So yeah, how do we do this? Now, immediately the problem is this is the spinner index. And therefore, it transforms in the spinner representation of the Lorentz group. And if we only knew gravity in terms of the metric, we would keep staring at it forever and not get any inspiration how to couple this to gravity. There just isn't a way, at least that I know of, where g mu nu and psi can make up together a Lagrangian which might have a Dirac term and an Einstein term and maybe non-minimal terms, and is generally coordinate invariant. The Dirac term by itself is not general coordinate invariant, it's only Lorentz invariant. That was quite an achievement already. It's what Dirac did.
Alpha runs from 1 to 2 to the power.
Well, that depends. I think for this purpose, let's say it runs from 1 to 2 to the d.
Integral part of dy.
Integral part of d by 2. It doesn't matter. We're never going to say what it runs over. When you actually have to do the calculation, that time you will need to. Okay. So now let's do one thing. Let's first establish a couple of formulae in flat space. So flat space time. So temporarily we are in flat space time, then we'll graduate to curved space time. In flat space time, the Lorentz transformation actually is a linear transformation where the coordinate just goes to this. I don't need frames. Frames and the space time can be identified. The frames can be thought of as delta A mu, that is for every A. Yeah. So this is Lorentz transformation. Yesterday we gave the property of this lambda. When it acts on the Minkowski metric, lambda transpose, that similarity transformation gives back the Minkowski metric. Now, I have in my notes chosen the spinner index to be called capital A, which is commonly done for higher dimensional spinners. Okay. So, under a Lorentz transformation, how does the spinner vary? And the answer is that it has 2 terms. One term comes from varying the argument and one term comes from the spinner index. The term that comes from varying the argument is lambda mu nu, x nu, del mu, psi a. And this you can understand from the fact that x nu del mu is a kind of a rotation in the mu. For fixed mu and nu, it's a rotation in the mu nu plane. If both of those are space, then it's actually a rotation. If one of them is time, then it's a Lorentz transformation. and it will be effectively anti-symmetrized. So that's natural, but there's another term, and that other term is key.
Nu and mu are anti-symmetries, right? No.
Yeah, but I think they're not necessarily, because in the case of Lorentz transformation they might be symmetrized. So that whatever property it is imposed by this lambda. If you were doing Riemannian, if you were doing Euclidean space, this would be anti-symmetric, because it would be the infinitesimal part of an orthogonal matrix. So we would write the orthogonal matrix O as 1 plus omega.
So this lambda is the infinitesimal part.
Lambda here, yeah. So, oh, good. Thank you. Yes. Because, oh, sorry, I made a mistake. I want to call this small lambda. Thank you. That was wrong. Delta x mu is equal to this.
So
Okay.
actual lambda is
And
1
so,
plus this small
yes,
lambda.
actual lambda is delta. This is the advantage of having one up and one down. Then the free part is delta. It's just Kronecker delta and then that. And one nice thing with orthogonal groups, since everything is real, there's no need to put an I, and there's no I, and it's just all straightforward. Good. So this plus something, which is what is acting on the spinner, and it is 1/4 lambda mu gamma mu AB psi B, where gamma mu is equal to the commutator of two gamma matrices, maybe with a half in my notation, half. Yes. Sorry?
How do we get the second expression?
Well, this is the definition of the spinor representation. So let me explain that. Actually, it's how gamma matrices work. The job of gamma matrices is to take a quantity that would be normally defined in a way that acts on tensors and convert it into a quantity which acts effectively on spinors. By effectively, I mean it represents the Lorentz group. So this is actually the representation of the Lorentz group, the spinor representation. This is the parameter of the transformation, because it's the infinitesimal parameter of the transformation. So we always dot the parameter with the generators. Okay. The only new thing here is that the generators, instead of being labeled, so this is analogous to TAIJ, where AB are like IJ. So they obviously act on something phi j, which is a vector of that group. A is represented by the pair mu, because it's the adjoint representation. So it's well, actually not adjoint. It's natural with orthogonal groups. A runs over 1 to dim G, dimension of the group, and it's natural to just think of it as a pair of indices.
This is the orbital part plus the spin part.
You could think of it that way, yes.
And like I understand the analogy, like it's completely analogous to that, but can you also like derive it?
I mean, well, this is the modern. If you ask how to justify the Dirac equation, the modern derivation is that you start with this and look for an equation invariant under this.
Okay.
It's just the modern way of writing Dirac's work, which was in 1 plus 3-dimensional notation. So if you just do it in 4D notation or covariant notation, you just get this. So this is a general rule that these are the parameters and these are the generators. And therefore parameters dotted with generators. So you can say this is like theta. In gauge theory you have theta A, Ta. So these are the theta A, these are the Ta. And together they must act on the vector. Okay. Good. So now what's invariant under that? Well, the free Dirac action is invariant. So this is, I mean, doing the calculation, of course, I'm going to obviously skip the calculation, but in my convention, this is the free Dirac action. I'm really not sure why I have a minus, but apparently there is one. I think that comes from the standard in minus plus 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 convention. You should have a minus, and that's it. So this is invariant. Under that plus that.
Is there any other term that we can add which will make this still invariant, or
Oh,
is
sure.
it just this?
No. You can add a million other terms. You can add.
No, to the transformation of psi.
Well, no. The transformation of psi is governed by the statement that it's a field in a certain representation. In the Yang-Mills case, you would have only this term. You wouldn't have the analog of this term because Yang-Mills transformation is not a space-time transformation.
It's a
And
gauge.
yeah, and it's an internal symmetry. Here, what we are doing is we are performing a Lorentz transformation on space-time. Now, actually, when we go to GR, we'll introduce frames. Once we have frames, again, we won't have this term. We'll just have this because what we'll be doing is rotating the frames at a point.
So these will be replaced by omegas.
Yeah. Wait. Give me a few minutes. What do you mean by omegas?
I mean, if you go from one point of space to some other point, it will depend.
No, we are not going to go from one point of space to another. My statement was, if I'm working in Minkowski, then it's natural to identify the frames once and for all with the space-time. Then there are no frames, and the only transformation is the Lorentz transformation, which actually moves points, rotates points. Okay, but if we are in a general relativistic context, then we will have a frame attached to every point, and we'll only rotate the frame. Then it's called a local-Lorentz transformation. Okay, and in that case, under a local-Lorentz transformation, the analogy with Yang-Mills is much better. There will be only this term. This is how a spinor transforms under a local-Lorentz transformation. That is for us the irrelevant part, which just takes care of the translation of the point. Okay, good. So up to here, so this is, if you like, a summary of Dirac's paper. Okay, in modern language. I don't think there is much more except, of course, the prediction of new particle and of antiparticles. But the statement is that this is invariant under that transformation, and it's a new kind of action. It needs gammas. Gammas generate the Clifford algebra. Clifford algebra is an auxiliary tool which helps us to generate representations of orthogonal algebra. That's its main purpose in physics, at least. Good. Now we want, yes.
Sorry.
Yeah, no.
Is there a term, also a term root G?
No, we are in flat space.
We are in flat space.
Yeah, now we are going to go to curved space. Okay. Now the question is how to couple this to gravity. This is exactly the question. Okay. Now, the first step is to realize that we can generalize del mu psi A, which is there in this equation. This has a del mu psi. Well, we should make it a covariant derivative. And what should it be? It should be the ordinary derivative plus a term. And this term is precisely omega mu, I think this may be what you are asking, omega mu AB, sorry, omega mu doesn't have spinor and this is gamma AB, there might be there's a factor there. So the statement is that when covariantly differentiating a fermion, I should get an answer where this quantity still transforms as a vector with respect to space-time reparameterizations and still transforms as a spinor with respect to local-Lorentz transformations. The first is guaranteed, even this transforms as a vector under space-time reparameterization, but this is not guaranteed because psi transformed with this stuff and this lambda is now in the general context is going to be a function of x. Okay, so if I differentiate psi, that derivative will act on this lambda. That will spoil everything. To correct it, I need a term like this, and this term, as you can see, has an analogous structure to that term. The connection always comes in a way which is analogous to the representation acting on psi, and this is precisely it. Yes.
And this is also like this gamma term is not there, right? Because it's like a scalar for
Gamma term. What do you mean?
Generally, when you are defining this del mu, there was this
capital
term.
gamma. You mean Christoffel symbol?
Yeah, Christoffel
Yeah, but
symbol.
there is no space-time index on psi.
So it's like a scalar for that.
Yeah, it's like a scalar for that. We will, maybe I'll write it or maybe not depending on time. You can consider what is called the Riemann-Schwinger fermion, which is got one vector and one spinor index. If that's the one I want, then I'll have a
That
Christoffel
term.
symbol term for it. Yes.
So this gamma AB is obtained by contracting with the field lines.
Actually, no. Good question. This is the fundamental one, because what was the definition of gammas in flat space? You remember that in flat space we had gamma mu, gamma nu, and T commutator is 2 eta mu nu. Now in curved space, this would not be covariant. You would have to put G mu nu of x here. Then your gamma matrices would have to be x dependent. That's not a nice thing. Then they are really not matrices, they are actually fields all over the manifold. So instead, we define gamma matrices in curves. I should have said that. Thank you so much. We define them like this, only local-Lorentz indices. And because of this, we still have exactly the same gamma matrices that we had before we went to curved spacetime. The flat space ones are the same. They can just be taken over. Now, if you want to write gamma mu, you are free to do it by taking a Fierbein EA mu and multiplying it with this. And then the x dependence is automatic because the frame has the x dependence in it. So actually in formulae, in supergravity papers and so on, most often this gamma A will appear and not gamma mu. Precisely because this is the one that's constant, not that. I think for the first time in my life I'm discussing in a course the first thing I was taught about supergravity for my first paper in 1979. I had to learn exactly all these things in order to write it. Okay, good. So we got a covariant derivative, and now it's not very difficult to write the action. So now we want S of the Dirac fermion and the frame. The frame has to enter. Okay. So we have integral d dx. Then we put here an e. Normally we put root det g, but e is the root, the det of e. This e means det of e a mu. So, or actually mu. This is the one whose det is the square root of g. So this will be there. And then I put minus psi bar gamma. Now comes the fun. Now you have to put a gamma mu. And you have to remember that this is gamma mu of x. Because it's going to contract with a covariant derivative which has a space-time index. And it's this covariant derivative just defined here. Okay. Now, very often, and also in my notes, this is explicitly anti-symmetrized. So I'll write minus half of this plus half psi bar gamma mu. Still, no, not to the left, to the right. Derivative in mu pointing this way, gamma mu psi. See, in flat space by partial integration, I can bring this to act on that at the cost of a sign. So here what I've done is I've kept half the original term and I've written half the term that you would have got by partial integration. The advantage is that then this acts on psi, this acts on this side. If I just kept this, then by partial integration this would also act on gamma.
It
And-
acts on the psi part, right?
Yeah, here it's because of this arrow, it means it's acting on psi bar, but here it's not.
From the right side and this
It's
thing.
acting on psi bar.
Yes.
I could have written it here also. Okay, and then there can be a mass term, and then there can be higher order terms if I want. And then, of course, I can also put, I don't know, 1/16 pi g or whatever r of E, the Einstein term. I can put a cosmological constant. So all that is, of course, allowed. So I think the point is made that the way fermions get coupled to gravity is to introduce the introduce frames, spin connection, a covariant derivative which is the correct one as per orthogonal groups for acting on a spinor representation. The covariant derivative we had earlier, which had only omega and no gamma, was the one for acting on the vector representation. So all the small a and b indices we have always had are in the vector representation of the Lorentz group, and the spinor is a different representation. So it needs these gamma matrices.
So,
Yeah.
So here
Can-
you express this R in terms of these frames, right?
Yeah, that is, of course, that was the one we had this Riemann, we wrote it as, so this is the Ricci scalar, which is obtained by tracing the Ricci tensor, which is, okay, so good. So I could take, the natural way would be to take R mu AB. This is the one which was a two form and matrix valued, and then multiply it with E A mu to contract these two, and E B nu to contract these two. And this already was expressed in terms of E, because it was expressed in terms of the spin connection omega, which is expressed in terms of E. So everything's in terms of E, and this is R of E. And that's the Dirac theory coupled to gravity. I'm glad I was able to do this today, because I think it's conceptually, it really teaches us something cute about frames. Namely, if we want to couple fermions, there really is no other way. Yes.